that you have gone through my previous lecture, which is about the probability generating functions. So in that case, we discuss with you how to develop the probability generating functions, especially for the discrete random variables, right? And then we discussed about some of the characteristics of probability generating functions. So today we are going to discuss how you can incorporate the concepts of probability generating functions into stochastic processes. So if you can remember, in stochastic processes 1, we discussed a concept about randomly stopped sum. So in that case, if you can remember, the most common example that we discussed was the ATM machine. So we know if you take the ATM machine within a given day, there are so many customers are coming to use the ATM machine. So if we just assume that we are using the ATM machine for the purpose of withdrawal, so there are number of customers who are coming. So if you take a specific day, a number of customers who are coming to withdraw money is a random number, and the amount that they withdraw is also random, right? Because different customers are withdrawing different amounts. And also if you take, let's say there are 5 customers on Monday, but Tuesday can be more than 5 or less than 5. So the number of customers and also the amount that they are withdrawing, both are random variables. So in that case, we were interested about the total amount of money that is withdrawn by the number of customers per given day. Because if you are the owner of the bank, if you want to maintain your ATM machine, you have to place sufficient amount of money in your machine. So in that case, you need to know the average value per day that the customers are withdrawing. So that total money withdrawn by n customers per given day is known as the randomly stopped sum, right? So in that case, if we just go with the usual notation, so if you take for a given day, if you have capital N number of customers, right, and if you take customer I, the customer I, let's say the customer I is withdrawing xi amount of money. So that is, the first customer is withdrawing x1 amount of money, second customer x2, likewise nth customer is withdrawing xn amount of money. So since we are interested about the total amount of money withdrawn by this n number of customers, that is equal to x1 plus x2 plus up to xn. So this is the randomly stopped sum, which is denoted by capital Tn. So actually in this case, we were interested about the expectation, the mean value of money, right, the expected value of Tn, and also the variance of Tn. So if you can recall what we have discussed in stochastic processes 1, so there we discussed the expected value of this randomly stopped sum, that is the expected value of Tn, that is equal to mu times expected value of n. So this, if you take this mu is the expectation of this random variable x. And when you take the variance of this randomly stopped sum, by using the total variance formula, we can show that it's equal to sigma squared plus sigma squared into expected value of n plus mu squared into variance of n, where the sigma squared is equal to the variance of x, right? So this is what we found by using the ordinary probability theorems, that is by using the law of total expectations and by using the law of total variance. So let's see whether we can derive the same thing using the probability generating functions, right? So in this case, the one thing, if we are going to solve this problem using probability generating function, one important thing is we need to find out the probability generating function of our random variable Tn. That is our first task. That is, we want to find out the probability generating function of the randomly stopped sum. So for that, actually we are using this theorem. So that is, if you have n number of random variables, let's say x1, x2 up to xn. So if these are independent and if these are identically distributed, and if these random variables are having a common probability generating function. So we know when you take the amount that the in number of customers are withdrawing, it's independent and also that is identically distributed. So we can assume that is having x's are having a common probability generating function. So let's take the probability generating function of x's as gx. So capital N is also a random variable, the number of customers. So if you take Tn as x1 plus x2 plus up to xn. So when you write the probability generating function of Tn, that is gTns is equal to gngxs. That is, if you want to find out the probability generating function of the randomly stopped sum, first you have to find the probability generating function of random variable x, and then you have to replace that. You have to take that as a variable when you are finding the probability generating function of randomly stopped sum. So we can actually easily prove this thing. So if you take, we are actually interested in finding the probability generating function of random variable Tn. So if you just write the probability generating function of Tn as, that is the expected value s to power Tn. So we know Tn is equal to x1 plus x2 plus up to xn, and these x's are depending on random variable capital N. So I can rewrite this expectation as expected value of s to power s1 plus x1 plus x2 plus up to xn, given n is a random variable. So you have to take the conditional expectation since x's are depending on n. So if you use the total if you use the law of total expectation, we can write the expected value of this, because here you have two random variables. You have x's and the x's are depending on capital N. So we are going to use the law of total expectation. So that is, we have to take the expected value of this term, and then we have to take the expectation of this whole term with regarding the random variable capital N. So we know when you have a probability generating function with the summation, we can replace that with the multiplication we discussed last week. Alright, so we can write this as s to power x1, s to power x2, likewise up to s to power xn. So the summation, we replace it by the multiplication, and then we know these x's are independent of n. So we can just omit the condition, right, and write this as the expectation. And then when you, since you have a multiplication here, and since the x's are independent, we can give the expectation to each and every term independently. That is expected value of s to power xn, expected value of s to power x2, likewise up to expectation of s to power xn. So you can see, if you take expectation of s to power x1, this is the probability generating function of random variable x1, and when you take this is a probability generating function of random variable xn. But we know these are, all these x's are having a common probability generating function. So here you have n number of probability generating functions. So we can write this is equal to the probability generating function of x, that is gxs, and we have n as big exponent since we have n terms, right? So in this case, so that now we are going to take the expected value of this function with regard to random variable capital N. right? So we can see that is, in other words, we are going to take the probability generating function, where inside the probability generating function you have the probability generating function of x as your random variable, right? So this is the proof, so you can easily prove that. So let's see how to solve this question, right? So in this case, right, in this case, if you take x1 up to xn, they are random variables, independent, identically distributed, and we want to find the mean value of Tn, right? So that is, in other words, we want to find the expectation of Tn. So we know, if you know the probability generating function expected value, you can differentiate the probability generating function and substitute 1. So the probability generating function of Tn is given by Gn Gxs. This is what we proved in the previous theorem, and then you have to substitute 1 for the differentiation. And then, so if you want to differentiate this function, first you can differentiate this function with regard to n, right? You can differentiate this function by random variable capital N, so that is g dash n. So within brackets, again you have a random variable, that is x, so that again you have to differentiate that with regard to the random variable capital X, so that is g dash xs. So you have to substitute the value 1 for s. So in this case, if you substitute 1, here you have gx1. So we know in the last lecture we discussed, for any random variable, when you substitute 1 for the probability generating function, it's equal to 1. So gx1 is equal to 1. So you have g dash n1 into, here when you substitute 1, g dash x1. So then g dash n1 means you are taking the expectation of the random variable n. And here you are taking the expectation of random variable x, right? So this is what actually we received when we use the ordinary method to solve this. So we get the same answer using the probability generating functions as well, right? So let's see another example. So this is the example of Heron goes fishing. So it's like this. Now there is a pond, right? So in this pond you have so many fish, right? And then this pond belongs to a person, and this person has gone somewhere, so you need to feed for this fish, right? So but one day when you come to visit this pond, you couldn't find any of the fish who were inside the pond, because Heron has visited this place, and Heron had been eaten all the fish in the pond, right? So that's what this says, right? My aunt was asked by her neighbors to feed the prize goldfish in their garden pond while they were on holiday. So although my aunt dutifully went and fed them every day, she never saw a single fish for the whole 3 weeks. So it turned out that all fish had been eaten by a heron when she wasn't looking. So here the capital N is the number of times the heron visits the pond during the neighbor's absence. So if you take, right, so the capital N is the number of times the heron visits the pond during the neighbor's absence. That is when this aunt is not visiting the pond, right? So the heron has visited the pond and has eaten a fish. So capital N is the number of times that the heron has visited this pond when the aunt was not there, right? And this it says this capital N is having a geometric distribution with parameter 1 minus theta. Why? So what is this 1 minus theta? So that is, in this case, it has assumed that the probability that this heron can find a fish in the pond is theta. So the heron is continuously visiting the pond until until the heron can find at least one fish, right? So when the heron couldn't find at least one fish, the heron is stopping. The heron is not going to visit the pond again, right? So that is, this is happening until the heron meets until the heron meets a success. So the success is, what is the success? There is no fish remaining in the pond. So if you take theta as the probability of eating a fish or having a fish for a given day, 1 minus theta is there is no fish in the pond, right? So if the success is having no fish in the pond, that is the probability of the success is 1 minus theta. So the heron is coming, visiting the pond until the heron couldn't catch at least one fish. So that is why the number of days is having a geometric distribution, right? So in this case, so this number of days can be equal to 0, 1, 2, likewise. Okay, so here what you have to find is, when the heron visits the pond, it has a probability P of catching a prize goldfish independently of what happens on any other visit. This assumes that there are infinitely many goldfish to be caught. Find the distribution of T, that is the total number of goldfish caught. So if this heron is coming today to catch a fish, no matter the heron was being able to catch a fish or not, second day, that is independent of what has happened today, right? So because of that, if you take today, sometimes the heron will be able to catch a fish or not. Tomorrow also will be able or not. We never know. So each day is independent. So if you were able to catch one fish today and tomorrow 0 fish, again on the next day you can catch another fish. So likewise, if you want to take the total number of fish that the heron caught, so that is denoted by capital T. So how we are going to solve this? So what we are going to do is, we are going to take a random variable capital Xi, where Xi is equal to 1 if heron catches a fish on visit I, otherwise it's 0. So since we are interested about the total number of fish caught, so if you take x1, that is on the first day, if heron catches a fish, x1 is equal to 1. If not 0. So you have a summation of ones and zeros, and ultimately, right, you'll get the total number of fish that the heron has caught, right? So this is what we are interested. So this is like a randomly stopped sum, right? So we know if you take the probability generating function of this T, that is equal to what we have proved, Gn into Gxs. So now we are going to find out the first one, that is, we are going to find out the probability generating function of x. So x is equal to 0 or 1 for a given day, that is, x is having a binomial distribution, in other words, right? So how are you going to find this? Now Gxs, that is the probability generating function of x, is equal to expected value of s to power x. So x can take only two values, 0 or 1. So s to power 0 into probability x equal to 0, s to power 1 into probability x equal to 1. So since this is coming from a binomial distribution, s to power 0 is 1. Probability x equal to 0. Right? Probability x equal to 0 means you have 0 successes. So this is a probability of a failure. So we have noted that the probability of catching a fish is p. So that is probability of not catching a fish is 1 minus p. And here you have s to power 1 is s. Probability x equal to 1 is probability of a success, that is catching a fish, that is p. So s into p is ps. So you get the probability generating function of x as 1 minus p plus ps. Alright. So now let's find the probability generating function of n. Okay. So n, what is the probability generating function of n? So n is the number of days that the heron has visited the pond. Right. So if you want to find the probability generating function of n, so we can write it as r to power n multiplied by the probability of n. Right. So we know it is given that n is having a geometric distribution. So the probability we can find 1 minus theta into theta to power n. So 1 minus theta you can take out since it's not depending on n. So you have theta r to power n, where n goes from 0 to infinity. So for this is the geometric series where you can apply the summation. So that is 1 over 1 minus theta r. So here you have 1 minus theta. So when you simplify, you have 1 minus theta over 1 minus theta r. Right? So in other words, if you take the probability generating function of t, that is the randomly stopped sum. So we have proved the probability generating function of the randomly stopped sum, but you have to take its probability generating function of n, and there the variable you have to replace by the probability generating function of x. So here the probability generating function of n is this one, and the variable is r, and the probability generating function of x is 1 minus p plus ps. So what you have to do now, this one, the variable is r you have to replace by the probability generating function of x, because that's what we have proved here, right? Here the randomly stopped sum probability generating function, you have to take the probability generating function of n, and the variable you have to replace by the probability generating function of x. So what we are doing is the same thing. So you are going to take the probability generating function of n, this one, and r we are going to replace with probability generating function of x. So that is also we have already found, that is 1 minus p plus ps. So what you are going to do here is substitute 1 minus p plus ps for gxs. So when you simplify that, furthermore, you will get a equation like this, where for your numerator you have 1 minus theta, and for your denominator you have 1 minus theta plus theta p minus theta ps. Now this is what we can receive after solving this question. That is, this is what we received as the probability generating function for t. But what we actually want to find, we want to identify what is the distribution of t. Alright, so if t is having a geometric distribution, the probability generating function is in this form. It should be 1 minus phi over 1 minus phi s, because the probability generating functions are unique. So if you can see the features of each and every distribution's probability distribution functions, probability generating functions, we can identify the type of the random variable. So if you take this one, here you have 1 minus theta, and in the denominator you have 1 minus, but you can't see theta s, you have theta ps. So we are going to restructure this again. Alright, so we'll keep this theta ps part here, because since we have phi s here, and we'll take 1 minus theta plus theta p as one term, and we are going to divide the numerator and denominator both by 1 minus theta plus theta p. So when you take the denominator, here you have 1 minus theta plus theta p. When you divide this by this one, you have 1 minus. Then again you have theta ps divided by 1 minus theta plus theta p. But if you take this one, you can't divide. So what we can do is, we can add theta p and subtract theta p. Then this term you can divide by 1 minus theta plus theta p, that is 1. Then again you have 1 minus theta p divided by 1 minus theta plus theta p. Right? So if you just write it in proper way, you have 1 minus theta p divided by 1 minus theta plus theta p. Whole thing you have to divide by 1 minus theta p into 1 minus theta plus theta ps. So this is like now the probability theta. So this is like 1 minus theta divided by 1 minus theta s. So it shows you the characteristics of the geometric distribution where theta is this one. Right? So that is, we can see the geometric distribution of 1 minus theta is this one now by solving this thing. So that is, in other words, this t is having a geometric distribution with theta 1 minus theta into 1 minus theta plus theta p as the parameter. So this is how we solve when it comes to the stochastic processes, how it's very useful when we use the probability generating functions, right? I think it's clear for you. It's very easy to use the probability generating functions when it comes to these kind of problems in stochastic processes. But why we use this probability generating functions rather than using the ordinary methods to solve these type of questions, right? So I'll show you why. So if you just want to find out this using the ordinary method, right? So we know capital N is having a geometric distribution. So we can write the probability mass function there. And then we know x1, x2, they are having a binomial distribution. So we can identify the distribution function. And then we want to find the distribution of t, where t is the randomly stopped sum. So in this case, so if you want to find out the value, so we want to find out the probability where t probability of capital T is equal to t, or in other words, if we are not using the probability generating function to tackle this problem, right, we have to start from the probability function. We have to define what is capital T, right? So the capital T is depending on capital N. So if you are going to find out its probability, you have to take the conditional probability here, right? So luckily, we can, in this case, actually we can write the conditional probability of this one, because capital N is fixed here, right? And x's are having a binomial distribution, but it's not be the same thing in each and every case, right? So in the most of the cases, the x value, it would be difficult or impossible to write down the distribution of x1 up to xn. Right, because here t you can replace by x1 up to xn. Again, then you have to find the probabilities here. So you have to write all these statements. Here you can replace the statements by the binomial distribution. But you know, you can see it's a hassle. You have so many calculations to do. Right, you can obtain the same answer by using so many calculations. So it's a difficulty, right? You have to just go through so many calculations, and sometimes it's hard to do manually as well, time consuming. But you can see when you use the probability generating functions, it's very easy to solve, right? So that's why in the stochastic processes we are using these probability generating functions. So there are some of the properties of the probability generating functions that we have discussed so far. So that is, when you take the when you take the any random variable, if you want to find out the probability generating function, which is denoted by g, right? So if x is the random variable, the probability generating function of x is denoted by gxs, where that is equal to expectation of s to power x, right? So actually in this case we are going to talk about only discrete type random variables. So if in that case, if you want to find out the expectation, you take the probability generating function, differentiate that and substitute 1. And if you want to take any other moment, right, the expected, what you have to do is, if you take the k, if you differentiate this by k times, and if you substitute 1, then you get expectation of x into x minus 1, likewise up to x minus k plus 1, right? And then we can find the probabilities using a probability generating function, right? So that is, if you want to find the probabilities, you have, if you want to find the probability of x equal to n, that is equal to, you take the probability generating function, differentiate that by n times and substitute 0 divided by factorial n. For an example, if you want to take the probability of x equal to 2, you take you take g double dash x, and then you substitute 0 divided by factorial 2, right? And then when you have a summation, if your random variable is a summation, and if you're interested of the probability generating function, that you can replace by the multiplication of the probability generating functions if the variables are independent, right? So these are the things that we discussed so far. So I think by now you have a good understanding about the probability generating functions of discrete random variables, and as well as how we use those concepts in stochastic processes, right? So as I told you, I'm going to upload very short videos, then you can take your time and grab the concept. So I'll stop from this point and I will upload this note as well. So if you have any question, as always, you can raise them, right? Okay then, thank you so much.